Okay. So, where are we with the homework? Fifth. Are we happier with the fifth homework now than before?
Yeah.
Yeah. How many documents did you judge?
Me personally, the 600.
Oh yeah, all of them?
Mm-hmm.
And the teammates?
Mm-hmm.
So you could run evaluation then?
Mm-hmm.
Is that done?
Yeah.
Demo?
No. I'm still doing class.
Oh, that's good. So we have what, 2 more weeks roughly, and 2 more homeworks roughly. Although these homeworks are, I cut one exercise out of them. So before I connect my projector here, let me recap where we are. So we're talking about machine learning for text. I'm going to talk a little bit about machine learning for the people who didn't take a machine learning class, to have a little bit of background of how this stuff works, but not enough to substitute a machine learning course. So if you plan to take a machine learning course, that's the right way to do this. So the first part that we said last time is we have an index, or we have raw data, raw text, and we have some sort of labels or annotations, tags, which could be relevant judgments, or it could be simply some other annotations. By machine learning here, I mean supervised machine learning. From this, to run machine learning, we need to produce a feature matrix. Even if some package says, just give me the raw text, I'll do machine learning with it, internally they have to produce a feature matrix. It's typically numerical. So in a feature matrix, like we said, we have document 1, document 2, up to document n, feature 1, feature 2, up to feature, say, D. And in here, this is the document I, component J. This is a representation of this document. So these numbers here, Dij, is the coordinate or the numerical value, feature value of document Di. This is a vector here, a coordinate feature value in position here. For attribute J. Now that's true for all machine learning. It has rows corresponds to observations or objects, and columns correspond to features. For example, the most basic stuff for Unigram, we have bag of words representation. Dij is what? The term frequency of the document I and term, say, word J. The most basic idea is to put just the count, which would imply very sparse, if we do so. Because if we use a term frequency value, most of those values will be zero. So I want to emphasize something here. In a lot of data problems in this course, but also very likely what you're going to hit next, whether it's an interview or an internship or a job, you're going to deal much more with how to produce a feature matrix and how to evaluate results, then you're going to deal with the core machine learning algorithm. I would say it's extremely unlikely that you're going to go on the world tomorrow and you're going to come up with a new learning algorithm out of a sudden. That can happen. That the people modify learning algorithms, and you might get there. All I'm saying is a lot of the jobs and research and data problems are not into how to modify a learning algorithm. A lot of jobs and a lot of problems are into how to set it up, how to create a proper feature matrix, how to evaluate the results, how to know when it failed, why it failed. Very few jobs and positions are into create a new learning algorithm. Probably none. So the most, since I'm saying that, the most effort into coming up with new algorithms, it's not for problems like this. It's for different kind of problems, different kind of machine learning problems. Okay, so our first task is to figure out this feature matrix, how to produce it, how to produce it efficiently. This matrix could be quite doable in terms of size and storage, even if the number of documents and the number of features is very big. So it's not uncommon to work with 500,000 documents easily and 100,000 features, yet the stuff can run on a laptop. So that's the first part. Then we need to, of course, train an algorithm, machine learning algorithm, produce a model, and then test the model. Test, model, or do predictions if I'm in a production mode, and do evaluations. Now, these algorithms here, I would say, pedagogically speaking, they fall into three classes. Last time we mentioned, I think, two of them. There is the first simple ones that you have to know to do any sort of data science. If you know, I know some of you didn't take the machine learning class yet and you plan to do it. Or you take a data mining class where you got a washout version of these algorithms. The truth is, if you want data science, you gotta go with those three. Cannot move anywhere without those three. Linear regression, decision trees, and naive Bayes. That's the simple stuff that you gotta know. I'm gonna add something here that's not supervised machine learning, but it's also one of these basic foundation blocks, which is K-means clustering. Now those are very simple things. You don't need to take a machine learning course to understand how how these algorithms work. Perhaps there are some fancy details about regularizing regression that need to be maybe not easy to understand by yourself, but I would say if you plan to be a data scientist, you gotta have a hold on those 3-4 things first. But then there's other things for which I would say it's hard to learn them by yourself. For these other things, you probably need to take a course. Those are boosting, ECOC, and neural networks. We can add SVM in here, or vector machines. So I would say the first part, you can probably read a lot of it by yourself. By the time you hit these in a machine learning course or other places, you just focus on details. This stuff in here requires this foundation, cannot be done. You can't jump into boosting if we don't know decision trees. But it's probably too sophisticated for somebody to take on by itself. And then there is the very fancy stuff, which is deep learning CRF. Multi-label problems. There's other things here. The deep learning is particularly useful where I have different representation of the data. So this bag of words representation, I can use deep learning on it, but it's not going to give me an advantage necessarily. There's sophistication into deep learning networks, in particular LSTMs, for example, right? That use more than just a bag of words. We have to understand that for text, a bag of words representation will lose meaning. In other words, if I tell you, here's a document, but I don't show you the document, I show you word counts. So the bag of words representation, I say this word appears that many times, this word appears that many times, so on and so forth. You could get the idea of what the document is about, roughly. But you inevitably lose some meaning of the document that's represented in the order of text, in the sequencing, right? So that's where a lot of these algorithms would fail, but deep learning might succeed if we implement it in certain ways. Now, I don't have to have just unigrams in my matrix. So another representation might be, unigrams plus bigrams plus trigrams. And if I do this, then Dij here will be some matching function between document I and a certain, let's call it skipgram J. In other words, my features here, I only have the unigrams in the bag of words, but if I expand to bigrams and trigrams and perhaps other skipgrams, the feature values will be more than just DF, will be some sort of match. The common sense is that the shorter the skipgrams are, the more I want to count for quantity for TF values, like how many times it appears. The longer I have the skipgrams, the more I want to count for the match. For a 5 gram or 6 gram, doesn't make much sense to count it how many times it appears, but rather how well does it match, because a 6 gram, there's one thing to match it verbatim, but you could match loose. This is very close to the proximity ideas that we've done in like second week or third week of class. If I have a 5 gram, and probably when I put a feature value, is not the quantity, how many times I see it, but rather how well it matches. So how is unigrams, bigrams, and trigrams related, between having total order of the text and having just a bag of words representation? Where is this stuff? So I'll say here, bag of words, that's the simplest one. I'm adding skipgrams here. So skipgrams do capture some of the order of text, right? Not perfect, but it does. And then I can have full sequence. Full text sequence. Where I have complete order. This representation recovers the actual text apart from stop words. So where is this? How rich is this representation with, say, bigrams between this and this? Obviously, it's better than bag of words because it contains all the unigrams and more. It contains some sequencing, right? We have Virgil Pavlov Northeastern University, that's a skipgram. And the feature value for that feature will be how well the document matches this particular skipgram. Or I can have full sequence representation, so I don't lose any meaning of the document by order. So my question is, how good is this? How much further from bag of words is this one with bigrams or trigrams? And how close is to this? Right. do I need a full sequence when I can use trigrams? Is trigrams a good enough approximation of full sequencing of meaning? Yes?
So I feel if you use n-grams, it would only generate dependency depending on the length. So if you have sequence of 4 words, but the true meaning of a sentence is implicitly conveyed through the 5th or the 6th word, you aren't really getting the meaning. You are just comparing the sequence.
Just to be clear, when I'm matching a 4-word skipgram, which I say I invented manually, Virgil Pavlo, Northeastern University, that's a 4-gram, right? I'm not necessarily limiting the window. I'm not saying, I mean, you could, with the matching function, say, I'm only count matches within 10 words. So those 4 words of the skipgram has to be within 10. That's in Elasticsearch the slope value, right? That says you have to have so many other words. But without a limitation, I could say match it within 20 words or 30 words. So then I do have a matching value for my 4-word skipgram into a window of 10 or 20. Maybe it takes computationally more time. But I don't get the 0 value. The idea of matching is to get a high value when those 4 words match very tight in text, slope 0. And lower values as they do match in text, but loosely. Like I see those, say, 4 words within a window of 20. So I want to be clear that when I say a 4-gram, I'm not limiting the matching aspect of the skipgram. I could still match the skipgram within the whole page or the whole chapter if I want to. What I'm limiting is what? When I say 4-gram. I'm matching 4 words, not 5. So if the meaning is captured by 5 words, I'm not going to get that meaning because I'm only matching 4. But the matching function, especially a fancy IR matching function, could match those 4 words within the whole document. It is true what he's saying, that some matching functions are limiting by the slope, which is equivalent to a window. If I have a slope of 6, it's saying I'm only going to consider matches of the skipgram you give me within 4 plus 6, 10 words. Everything that's outside this window, not a match. But that's a parameter that I can set, right? And I think information retrieval is very good at providing efficient ways to do those matches. Remember that guy with the blurbs that you can check positions and he gives you the title span. He did it, the example was for 3 words, but you can do it for 4, for 5, for 6. So you get the titles match quite efficiently if you have an inverted index with positions. By now, it's not at all a computational problem to get long skipgrams, good matches, you know, how to match them. And I can match skipgrams in order or out of order. So with that clarification, that the skipgrams, I can still match them against the whole document if I want to, I'm back to my question, how far is this from this? In other words, I want to say, what kind of example and matchings I would go ahead with unigrams and bigrams, perhaps trigrams, but I don't need these. And when this is not good enough, I need a full sequencing of the words of the text.
So the unigrams are sequential. They are more useful when we are trying to use a sequence of words. But if you're using the semantic or the meaning of the sentence, a full text sequence would be more useful.
So we always use the meaning, right? What matters in text, it's the meaning. Text is a human language, right? It's not natural in the sense of, you know, we have a convention for how to express our thoughts. That's the meaning of text, right? So we always want, whatever we want to do is to get the meaning of text. But the question is, when is that meaning of text represented this way, at least good enough, and when it is not? Like even with trigrams or 4grams or 5grams, I'm not capturing the actual information I need to capture. Now, this is a philosophical question, okay? There's no good answer for this. But there are extreme obvious situations, right? When is the unigrams and perhaps bigrams good enough? A lot of factual queries, location, dates, numbers, quantities, where, what, who, can be captured with unigrams and bigrams, right? I mean, if I type Napoleon Bonaparte, that's a bigram, right? Any reasonable R function will produce a score that will give me a high value for when Napoleon Bonaparte, these two words, right, appear a lot in text or appear tight in text, and will give me a low value when there's no Napoleon and no Bonaparte in the text, right? This example, Napoleon Bonaparte, which is a famous, French emperor, right? It will work with bigrams, right? Because the meaning, whatever the document is about, whatever can be expressed with the words Napoleon Bonaparte refers strictly to whether it's about Napoleon or not, right? It's a guy who led France and conquered and got stuck in Russia, so on and so forth. You could say, do I need bigrams in this case? Do I need the Napoleon Bonaparte to be a bigram? I mean, can I do just to the unigrams, Napoleon and Bonaparte? In other words, I have two features, unigrams, Napoleon Bonaparte, and I have feature values, maybe TF counts, how many times I see Napoleon, how many times I see Bonaparte in those documents. Would it be useful to have a bigram Napoleon Bonaparte? The difference between unigrams and bigrams is that it will capture when the two words are together versus when they are not together. I would say probably in this case, bigram will not be very useful because the number of Napoleon and Bonaparte in text will give me a pretty good approximation of whether that's about Napoleon Bonaparte or it's about a different Napoleon. You guys following me? So a lot of factual based features, independent of what I'm doing with these documents, but at some point label is going to matter. What is the target that I'm learning and predicting? Could fit in here. Now, what is the stuff for which I need, full sequencing representation? Something that if I miss the order, meaning is lost.
Something like a classification problem. You're identifying which class a particular text document belongs to.
Class like in sports
Like
versus
soccer,
economics?
yeah, sports.
I would say, in my opinion, my guess, sports versus economics is rather one of the first two. As in, if my target is 20 news groups, data set classification, and there are like so many groups with sports, economics, entertainment, whatever they have, business, politics in there. Probably to make that distinction between those classes, I need to focus on few words or bigrams, and I can map a function, a learning model from these words or bigrams to the right class.
I meant within a particular class. So
To distinguish document
like if it's some article related to politics, is it a pro topic or against topic?
Right.
Or judgment of that thing?
Okay, that is true. Political discourse is the trivial example where without having the sequencing, and even with the sequencing, even for humans, it's hard to parse what the guy is saying, right? It may be that the unigrams and bigrams, in terms of, say, feature values, appear quite similar for two political documents or discourses, right? But the meaning in terms of political sense is different. I think I already mentioned this in class. Political discourse is one of the obvious cases where unigrams and bigrams will not be able to distinguish things. What else? Yes?
I don't know whether it will be right or not. The lyrics of a song, if you mess up the words, you wouldn't get the right lyrics.
Yeah, but what's the task? The label is identifying the song, or?
You want to get if you only know one line of a song, unless you type that line exactly, you wouldn't get the full text of the lyrics. So there the sequence matters, and you can't mess up the words.
You mean when you type it on a browser and they give you a set of results?
Yeah.
I guess what happens there, so what she's saying, what do I need to type in a Google box to get back the lyrics of that song? The difference being, do I want to type just a unigram from the song, right? Or some name or something in the song, or do I have to type a full verse, right, to get the lyrics? I think she's right in the following sense. That's independent of machine learning. I think she's right in the following sense. A lot of these lyrics, if you look at the words, they're common words. So you can't pick a word that immediately identifies the song, but the words in a specific order, right? What was that song? Hotel California, right? Neither Hotel or California immediately identify the song, but if I type Hotel California, that's the song, right? But do I need, back to my question, do I need this for that? Again, if I type Hotel California as unigrams, 2 unigrams or a bigram, would I get the song or not?
You have to type song along with that. Hotel California song. Then you might get it.
So, as I said, this is not a clear answer. Our goal here, is my goal is not to give you a clear answer. Is to make you think, what features do I need to do my task? Can I go by with unigrams, perhaps bigrams? For unigrams to bigrams, it's a smaller extension. And maybe to trigrams in a specialized domain, like in medicine, medical documents, a lot of them have to have trigrams because there is typically a part of your body that's a component of the trigram. Is it leg, arm, shoulder, whatever the problem is. There is some laterality, left, right, back, forth, something like that. And then there is the actual problem. It's broken, it's, surgery, it's like something. So in medical domain, a lot of trigrams are being used for this purpose. But to get to the full sequence, there's the problem of a meaning that cannot be captured by factual bits. There has to be the whole set to represent that meaning. Okay? All right. So now, back to machine learning algorithms. If I use full text sequence, it's not immediately clear how to use regression on that. Because regression needs a feature matrix, and there is no easy way to represent full text sequence with feature matrices, right? How about this? Can I do this in a feature matrix? If I have unigrams and bigrams and trigrams, how do I do it? Every unigram, bigram, and trigram becomes a column in my matrix. That might be a problem because the trigrams could be easily into millions, right? So if I expand this way, I have to be careful how do I manage my data there. Obvious example for bigrams being useful? Sentiment analysis. That's one of the classic examples where if I do sentiment analysis on text, bigrams versus unigrams make a big difference. But you'd be surprised how far the unigrams can take you. I mean, definitely when you have a classification problem, supervised classification, and you find that the label, something like economics versus sport versus politics, clearly depends on some unigrams, right? I mean, if I see, in this case, if I see things like LeBron James, that's probably about sports. If I see Donald Trump, that's probably about politics. If I see, Goldman Sachs, that's probably about finance. So if you have this intuition that my task, whatever I'm trying to predict, seems to be related to certain words, definitely try by unigram first. Because unigrams can take you quite far. But remember that if I move from here to here, I probably just change the feature matrix and stick with my algorithms, I can try. But if I move from here to here, I can't use, at least not immediately, some of these algorithms. Because to represent the sequence, I need sequencing. So there's ways to parse both text and images to preserve the sequence. These recurrent neural networks, that's not something we can do in this class, but you would need a representation to preserve that sequence. And sometimes it's not just about preservation, it's about extraction. like what sequences are gonna matter, since I don't know in advance what sequences are gonna matter. I have to pass a window through text and try all possible sequences. That's not easy to do. Okay, so now I'm gonna one more thing before I connect the projector. This K-means clustering, which we're gonna talk about next week more. Not K-means, but we're gonna talk about clustering on documents, on text. Of course, I'm assuming everybody here heard of K-means. I mean, even if you didn't take a class, right? A lot of clustering depends, of course, on similarity between two documents. So let's say D1 and D2. That's how a lot of clustering is set up, right? You need to know how similar two objects are, two documents, or how distant they are. People who took data mining, that's how we started the class, right? We said essential for clustering. And actually for machine learning, there's a theorem that says a lot of machine learning depends on how do you understand similarity between your objects. Stand on this. The reason I'm emphasizing this is that for information retrieval, we in information retrieval have much better tools to answer these similarity questions than basic data mining, right? In data mining, there is some representation in Euclidean distance or cosine, but information retrieval for text, if those are documents, provides much more interesting matching functions to determine how similar two things are. So that's where it can make a difference if you have a clustering task. Knowing information retrieval versus not knowing information retrieval may make a difference, because without information retrieval, what are the options for similarity? Cosine, Euclidean distance, and a few other mathematical functions. But if we use information retrieval, we can capture, like, just look at the Rouge metric for summaries. It captures very interesting similarities between documents. And there's an entire area of research that has to do with near duplication. There is a plagiarism, where I'm trying to figure out if something has been copied, maybe with some change of names, right? Or near duplicate detection, where it's not about being copied, but it's pretty much the same content. So those things are being studied in information retrieval, and we have all kinds of measures of similarities, definitely appropriate for text, not for other objects. Euclidean distance or cosine is appropriate for anything that's represented with numerical values. But for text, we can invent much more fancy similarity function. So we can have a chance of clustering documents much better than if we just apply naively, say, cosine similarity to them. Okay, I'm gonna connect this. And walk through some things. So a lot of stuff here we already seen. Feature matrix. A lot of what we want to do without machine learning could be written as some rules that people have come up to differentiate things. And you'd be surprised how many people actually use rules like this in a hospital, for example. A lot of how doctors or nurses or medical personnel makes decisions about patients are exactly rules like this. Heuristic that have been tried many, many times over many, many years, and they've been, decided to work. Banking was working like this for 300 years, right? How do you think a banker in 1800s, we came and says, I want a loan, right? I want to do something. How would a banker decide to give you a loan or not? They would say, oh, who are you? Oh, you are the king's brother. Okay, I'm going to give you a loan, Like, how related are you to the king? Okay, you're not a brother, but your cousin. I can't give you that much. I'll give you a lower loan, How big of your army? So you have a big army. Okay, I give you the loan because I think you're going to wipe out somebody and pay the debt, How did they come up with these rules? Bankers and doctors and everybody. A lot of trial and error, and a lot of observation, and a lot of what happens, right? Banking has changed in the last 50 years or so. Computers and mathematics change a lot how to interpret the idea of risk, right? What's necessary for loans, to understand exactly what risk you have of not being paid back. Same thing with medicine. Now a lot of the stuff in medical domain works in machine learning. But those are not bad rules. Here's this one that you're going to have in homework 7, is spam detection. If email contains enough of free words, I wouldn't say just contains, but maybe more than 2 or 3 times, and porn and some other things, probably that's a spam document, right? This is not a bad rule. It makes sense and it's probably accurate a lot of times. So what happens, what's the difference between extracting those rules manually with our intuition, what the doctors and lawyers and other people did, versus running machine learning? Machine learning might extract rule like this, right? Might be more exact, maybe we think it's age 22, but in fact machine learning can correct this rule and says it's actually 24, the number that you're looking for. The machine learning advantage is it can extract rules that humans would not think of, even experts in that domain. That happens a lot. Lawyers get surprised, doctors get surprised that the algorithm, machine learning algorithm, finds some rules that makes no sense to them. Those might be actually bad rules. The rules that makes no sense might be an overfitting rule, something that works for very, very niche objects because you don't have enough of those, so exceptions. So it does the classification job, but it won't work for the general cases, so that's just an overfitting. About machine learning, the general machine learning, we split usually the data into training versus testing. That's an academic exercise or a development exercise, because in production we don't really have testing. In production, once we have a model, we use it to make predictions for whatever purpose we need. But how do we do this in order to avoid biases? We do something called cross-validation. Right? That's a very simple thing. I think most people heard about it. I can chop this off not in 80% versus 20%, but I can chop it off into 5 chunks of 20% each. And then separately, take 1 chunk as testing and the other 4 as training, and then take the next 4 as training and 1 as testing, right? If I do that, I don't think I have that here. If I do that, chop it off into 5, they call folds. Folds 1, 2, 3, 4, 5. How should I exactly run? Like, how do I average all this stuff? I train an algorithm over 4 folds, test to check my performance on the 5th. Then on the second experiment, I do what? So suppose you're having homework 6, you have 20 queries. So let's say you have query 1, query 2, query 3, query 4, query 5, query 6, query 7, query 8, query 9, query 10. Then we have 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, into 5. So homework 6 is asking you to split this into 5 folds, 20 versus 5, right? So it's, 20 would be this, I can do this versus that. That would be one split. This is train, test. But then, second experiment, I can do this as train, and this here as test. What I mean here is the query document pairs. When I say query 1, I mean take all the documents that you have judgments for query 1. So what I average in the end, as in general machine learning, when I run this 5 times with each fold as testing, I have to measure the performance numbers before I average. So I run it 1 time, I get, say, accuracy or F1 or whatever my metric is. I run it again, I get another F1. Again, I mean completely from scratch. Retraining on the 4 folds, testing on the remaining 1. Then I do this, and this as training, and then test on this one. I get 5 testing performance values, which I can average after that. So that's to avoid biases. You could say biases is one thing, but then what happens if I shuffle the data? I could just shuffle the data once and chop it off at 80 to 20%. Even then, if there's a lot of outliers, it matters where these outliers fall into. So it's cross-validation. It's a pretty common technique for avoiding this. A lot of machine learning libraries that you can use. This is something we're gonna maybe talk about next week a little bit more. In information retrieval, since web is such a dominant exercise activity for everybody, people have recognized that machine learning objectives may not work very well because web retrievals, what Google does, it's not really a classification problem. It's a very, very skewed classification. So for ranking purposes, I may need a different objective than regression has or than the decision tree has. So people have come up with objectives that do performance appropriately for 1 or 2 documents or 3 documents relevant out of 10 billion, which measures like accuracy cannot capture properly. If I'm to run gradient descent until I optimize, even if theoretically possible, that will take a very long time to get a good model based on accuracy if my classes are so skewed. A good class of relevant is 2 documents or 3, and the other one is the rest up to 10 billion. So for learning to rank purposes, we may want to do something else. So none of this stuff directly gives me ranking objective, right? Regression is typically optimized for least square loss, right? Boosting. No, we don't know. But decision trees? Accuracy, right?
Yeah.
It's optimized for accuracy, matching the classes. How about naive Bayes? Naive Bayes, it's matching, it's trying to optimize a likelihood that corresponds to naive independence of the features, right? So assuming the likelihood as a probability function is naively represented as an independent of the features, that likelihood is optimized by naive Bayes. Boosting is a greedy procedure. I'm going to talk a little bit about that today. Quite popular for text because it's very robust. Boosting advantage is that it makes very little assumptions. As opposed to naive Bayes or regressions or other algorithms who are very good if the assumptions are satisfied, but if they're not, it can fail. Boosting makes almost no assumption about the data, and it can do quite well, in fact, surprisingly well. So So that's just how to run liblinear. I'm sure you guys can figure that out. Cross validation. Here's the faults. The rest of these slides are about, do I really want to take this as a bag of words representation? I mean, assuming I decided already to not use the sequence, right? So I'm not capturing the order. What else might matter here? Here's an example. Identifying some words as nouns or names or locations would help, right? I would like to know that something is a name. Identifying chunks of the document where they're coming from. One thing is to say, I have a certain name in the title, or certain name in, I don't know, summary, or certain name in a table, or certain name in a free text, or certain name in, I don't know, the ads or the menus. So identifying, this is the Virgil word that's in the title versus this is the Virgil word that's anchor text versus this is Virgil word that's just a body of the document, or this is Virgil that's in a footnote or a reference, would help, right? Would it? So we have a feature, Virgil, that's a unigram. What I'm asking is, do we want to have just Virgil and if we count how many, this column is a column of counts of that word into all documents, or we want to have two Virgils? This is Virgil in title, and then this will correspond to whether Virgil is in title or not for these documents. And this is Virgil in the body of the document, which will be a different feature. And another one will be Virgil is in anchor text. So that would be one for documents that have Virgil as anchor text. Anchor text is what you see as a link, right? It's not the link itself, but the text, HTML text display for the anchor text. Would this be useful? So we think certain things, like a name, a location, a date, would have a much different value as anchor text than a free text body of the document, or title versus not in title. If that's what we believe, then we would need to have separate features, because in a bag of words representation, we can't have Virgil separated, right? But we could create this feature matrix in a different way. We could have, in fact, people have done that. In fact, we have done that. Our group doing consulting for medical data. We distinguish a unigram coming from the doctor note versus a unigram that comes from the same unigram that comes from a different, not a note, but as an annotation with things like appointment, reason for patient visit, complaint. If a patient's complaining, patients write something, my tooth hurts or something like that. The word tooth in there, it's different if it's in a complaint rather in the report text. Because see, what happens if it's a dentist, all the reports of the doctors will contain the word teeth or tooth, almost all of them. But very few will have to do with a complaint, a specific complaint. So when it makes a difference, it's better to record it differently. So with that, let's go a little bit to the basics of these algorithms. We already did, right? We did two of them. I think we talked about regression. Yes?
I had a question about this. So, if you have a word in the title, wouldn't the body contain the same word a lot of times? So, those features will not be independent. They will always be dependent.
Right. So, I'll do two answers to this, right? We don't need to have independent features. So there's no requirement that this feature matrix have to have independent features. In fact, sometimes feature 1 and feature 4 are perfectly correlated to each other, right? It may be that every time you see Napoleon, you see Bonaparte, right? So if I have two features, Napoleon and Bonaparte, the counts on each document, how many times contains Napoleon, are exactly the counts of how many times documents contain Bonaparte, right? So for machine learning, this correlation makes the second feature completely useless because they perfectly correlate. Now about what you said, hey, if I see Napoleon in title, what's the point of looking in the body, right? Because very likely that word will be in the body. But how about the other way? It's the case that if I see Napoleon in the body, it's necessarily in the title. So by having two features, Napoleon in the title, Napoleon in the text, how many possibilities I have, theoretically speaking? 4, right? I can have documents that have no Napoleon in the title, no Napoleon in the text. Napoleon title, but not in the text. That's what you're saying, it's very unlikely, right? If it's Napoleon title, it's very unlikely not in the text. I can have not in the title, but in text. And I can have in both. So would it be useful to distinguish those two features, to not have just one Napoleon, unigram Napoleon and the TF counts, but rather have two Napoleons? To say, between two documents, I'm going to distinguish if one of them contains it in the title and the text, versus the other document who contains Napoleon just in the title, but not in the text. I think it will. I think if you can, this is something I learned from experience, but it's by now known to be true. If your objects in machine learning have a structure, like a lot of documents are organized with title, summary, I don't know, Wikipedia box, da 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 da, it's very useful to make use of that structure. But sometimes we cannot ensure consistency. The problem with these is that sometimes we get documents that have been already formatted somehow, and we don't know if that was a title or not. Like, what if I have 85,000 documents, and I can clearly tell this is a title for, say, half of them, but for the other half, I don't know if this is a title or not. Or maybe they're missing the title. Then it's hard to do this kind of thing if the structure of the data is not consistent. Same thing for images. If I can classify the images into, say, I know the source of the image, where it came from. I know what camera has been taken with. I know in what location this has been taken, so on and so forth. It's very useful to make use of that information if you have it and if it's consistent, right? If I have 1 million images and structure I have in only, I don't know, 10,000 of them, 1%, is not that useful.
How is it beneficial to have title in the feature matrix, given that the unigram count of that particular word will already be very high?
I'm not sure it'd be high. You think everybody who has Napoleon in the title has to have a lot of Napoleon in the text?
Yeah, the whole text was about Napoleon. So.
But he references
I think in many cases titles makes a difference, because you know what I may be looking for might be only the documents that have it in title but not in the body. If I don't distinguish two features, I'm going to have only one Napoleon from both title and body, so I wouldn't know when it's in the title or when it's not in the title. Do you follow me? So what if I need to specifically know where Napoleon is in the title or not? You could say, why don't you just use Napoleon from the title, ignore the body then? What if then Napoleon in the body is relevant as a feature for some other task or problem, but not necessarily if it's in the title? There are many questions that you can formulate in a way that Napoleon in the body will help as a feature. Right? We're talking about French history or French battles or something like that. That doesn't have Napoleon in the title, but a document that has Napoleon in text will clearly have an impact to that query or task. Okay. What I want to do is walk a little bit more through these. We already talked about two of them. I wanna make sure without taking machine learning class, that we have the basics of those three things. I cannot do anything about this in here. We have to go to 3 months of machine learning before we get to this. That's impossible because we only have 1 week left. But I want to at least make sure that the first part, even if you don't take an ML class, makes sense. So I'm going to start with decision trees because I have them here in this paper. I hope everybody understands how decision trees work. I'm having a classification problem. So the basic idea of a decision tree is extremely simple. I want to make a split. A split corresponds to pick a feature, and because it's numerical, sometimes they're categorical, but if it's numerical, I'm saying age is a feature, right? Is it more than 24, less than 24? So that's the kind of split that decision tree does. If it's categorical, say the brand of the car, I may ask if it's a Honda or Toyota or Nissan, go this way. If it's a European car, BMW or Opel or Peugeot or something, go this way. And I can have another branch. Decision trees are not limited to 2 branches at the split. If it's an Asian car, European car, or American car. I hope everybody can see that. It's the same kind of rule that doctors invented by themselves. If this guy has that much blood pressure, do something. If the blood pressure is below that value, do something else. Okay? So the other observation that I think is clear is that I can construct the whole path. Because I keep going with this tree, I'm going to end up with if the blood pressure is more than something, and this person works in an office, and this person has, I don't know how much sugar, and the age is more than 60 years old, and so on and so forth, right? I can combine these decisions that creates a path from the root of the tree down to a leaf. Okay? So a decision tree takes any data at the root and makes decision split by a feature and a threshold, say. It compares the features to the threshold, smaller goes this way, bigger goes this way, makes another split. That's another feature with another threshold, not the same one. That's feature 1, that's feature 2. And this one makes a split again, split again, split again. What's going to happen here? This is, let's not say here, let's say here. This split went right, right, left, right. So this is everybody who had age bigger than something, blood pressure lower than something, sorry, blood pressure bigger than something, sugar more than something, and some other property tested there. Yeah, so I can get the path like that in the data. These trees are greedy. Once they make a decision, they don't go back and change it. So the point of the trees is now like globally optimize everything until I get to an answer. I make the best decision I can here. If you study algorithms, you know what greedy means. And then I move on with that. How should I make the best possible decision? So what do I need to make a decision in the decision tree? How do I design off a split? So I need a criteria for how good a split is, right? Once somebody proposes a split, she comes and says, split it by that. I need to know how good that split is. That's a local decision because, again, trees don't make global decisions. They make the best they can right there. So I need a criteria for how good the split is. And I need a set of splits to try. Decision trees are quite dumb. They're not intelligent. They try all possibilities that you give them and pick the ones that is best by the criteria you give them. So it's literally a brute force idea right there. With every split, it says, from these data points that are here, try all the possibilities you give me, all the splits, all the possible features, thresholds, so on and so forth. I have a criteria to decide which is the best split for me right now, and I pick that best split. Easy. In fact, decision trees, I think, can be taught very easily without even mentioning machine learning. It's a kind of algorithm that makes a lot of sense computationally without realizing that you're learning something. So what? It's a, say, simple criteria. I have some data here, and how would I know if I get a candidate split, say, I compare a feature value with a threshold. I say, if the age is more than 24, go left. If the age is bigger than 24, go right. How do I evaluate such a split? I don't mean the mathematical formula, I mean the intuition. When a split is good, what should a split do to help out? What's my purpose with these splits? Entropy.
The labels are equally.
You're getting close.
Uniformity of the data is helpful.
What?
For example, diabetes, everyone who has diabetes should go on once a day.
Say again. Slow down.
Everyone who belongs to one particular category, all the data points that belong to one label should go on one side and
That's
another
ideal.
label on the other side.
That's ideal. The split helps if the confusion in the labels I have here. So I say I split those three classes. I have a confusion because at this point I have 30% class A, 50% class B, and 20% class C. Those are politics, sports, and economics. A split will help if after the split, the confusion is getting lowered. I have less confusion. For example, let's say that the split was 20, 50, 30 for the labels. What would be after the split a good result, a good progress? For example, if say the 20 and the 50 goes here, and all the 30s, the third one, so this is class A, class B, class C, A, B, C. Clearly I have less confusion now that I had before the split. Because at least now I know this guy, the class C, went the other way. It's only a confusion between A and B, right? How about if I say 20, so that was an obvious example, but suppose I have 20, 40, 5, and these guys of course have to be, in a decision tree, everybody goes one way or the other. There is no lost data point. So it has to be what in here? This is 0 for A, B is 10, and C is, what do you say, 30 minus 5, gotta be 25, right? Is that split making progress or not? I mean, it's not perfect. Let me write this nicer. Data classes A, B, C, we say 20, 50, 30. And after the split, suppose I get 20, 40, 5, and in here I have to get 0, 10, 25. Would we say this split has made progress? It is less confusion now in each node, or average on an average per node. Is it less confusion than it was before? Is it? Yes. That's where the entropy comes into play. I need to measure this confusion. How confused am I here? So there's a mathematical formula to say, if your distribution is 2045, here's entropy or some this information gain. There's all kinds of metrics that measure how random this stuff is. The less random, the less confusion, the better the split. So decision trees are easy that way. They just go through the splits that you indicate, or through all the splits if you don't give them a list of splits to try. And then they pick the one that has the best criteria for separation. But that's a greedy decision. It's not being reviewed. Once it's done, it's done. Yes.
Can they use the same feature again to make a split?
Yes. Because I could ask, is the age more than 24 or less than 24? Once the age is more than 24, I could still ask, is age less than 40 or more than 40, right? Out of the people who are age at least 24, I could have another split of people between 24 and 40 or more than 40. But can I make a split to the same feature in the same threshold? Would it make sense to ask the same exact question again? No. Do I have to worry about this in decision tree? Like, would the decision tree ever pick the same split again? If I allow it to try the same split, whatever split it was here, if I allow to try the same split, would it be the split that's being chosen? No, why not?
Because the confusion is the same.
Confusion will be the same. Whatever data came this way, all the data, but if I try the same split, will go on one branch, and then whatever I had here will be here. That will not help reduce the confusion of the labels. That's called information gain, by the way. This reduce, how much do I reduce the confusion of the labels? And this is a decision tree. It's based on the ideas that those are counts of labels. How many of class A, how many of class B, how many of class C do I have? But suppose I have, instead of these labels, I have salaries. So I'm trying to predict a salary. That's a quantity. These are counts for sports, economics, and business. Suppose I have, instead of this, salaries. I want to create, that's called a regression tree, where the criteria is based on a quantity. How would I do this if I'm trying to deal with salaries? Yes.
Variance.
Hmm?
Variance.
Right, so I measure the variance of all my salaries here, and then I try to find a split. Same idea. Try all the features of the ones I try, or the ones I list as possible candidates, and then say measure the variance in here of salaries and the variance in here, and the split is good when the variance after the split is small, right? So you can see how this goes. Maybe I have here few people that have very poor, low income salaries, and few people that are, rich, they have big salaries. If I find a split that distinguish them, the low income versus the high income, both variances will be small, but the original variance was quite large. So in the regression tree, this whole mechanism stays the same, except for the criteria to evaluate the split. It's based on a quantity variance of quantities like salaries, rather than categorical, how many of that label do I have? Okay. Like I said, you should remember that decision trees are pretty close in nature to what humans come up with, those heuristic rules that you might see in the data. Those rules are similar to what the tree-root rules. Okay, we talked, I think, about regression last time. And I think most of you have seen regression anyway. What I'm going to bring up about regression is the logistic regression that's necessary for classification, because regression without logistic function predicts a quantity. Right? Here, it's a derivation, and this is the gradient descent rule that updates the regression coefficients. This is not a greedy method, this is a globally optimized method, because in the end the coefficients are the global optimum coefficient. We can show this quite easily because the objective is convex. So it has the property that a local optima would be a global optima. The update rule is very easy. I'm sure you can follow those derivatives quite easily. This is a very simple derivative of a quadratic function. So what's up with the logistic function? Logistic function transforms the scores into probabilities, fake probabilities, because they're not They just, I determine what score corresponds to what probability, right? So depending how I set up, how sharp this function is, I control the probability sensitivity. But how do I use the logistic function on top of regression with gradient descent? No big deal. I have to do a compound derivative, right? So instead of differentiating that h function, I do g of h, where g is the logistic function. And I have, some derivations here. And I obtain, you can go, I would say you should go over this derivation, make sure you understand it. You don't have to remember it, but this is just a very, simple manipulations with the derivative. And then I get a different update rule, which is for logistic regression. But it's the same exact idea as with linear regression, except the function is not sum of wx. It's the logistic transformation of wx, so it's a compound derivative. And by the way, you should know that you should know gradient descent. It's an absolute requirement, even if you didn't take machine learning. But you should also know there's better numerical optimization methods than gradient descent. Now, this is not required to know what other methods to use, but in production algorithms, almost nobody uses gradient descent. So that's what I have to say about regression. It's just the same derivation with a logistic g on top of it, so you need a compound derivative. Okay. So before I talk about naive Bayes, boosting is a little bit of a, I wouldn't say combination between decision tree and regression, but boosting is trying to add up a bunch of trees. So here's how boosting works. Here's a tree that I create, a tree with splits. Generally, the last one indicates prediction, the leaf, right? Because if I don't split anymore, means everything that got to that point gets a certain value of prediction or score. Can I add this to another tree? And with another tree, and improve performance. In other words, I don't want one tree, I want multiple trees. This guy produces a score or a classification. This guy produces a score or a classification. This one produces a score or classification. And I have a way to combine the trees to get my overall score and classification. And if that's possible, is it better than just producing a deeper tree? I mean, can I get the same result by just expanding the first tree a little further? Contrary to most people's intuition, which was that by adding a bunch of trees, you don't get much. There was a breakthrough in machine learning about 15 years ago, 20 years ago. And a big guy now, big name, showed that this idea has a lot of potential. You can use simple trees. You don't have to expand them too much, but when you combine them together, you get a huge advantage. The reason I'm saying, to me, this sounds a little bit like regression, is because the trees, of course, are decision trees, like before, but adding them up, perhaps with some coefficients. Let's say I give this guy a coefficient alpha 1 plus alpha 2 times this plus alpha 3 times that. That sounds like a regression now, right? Is whatever comes out of data, this is not a feature value, but it's kind of like what's in the data there, right? If I do a split, it's depending on the document times the coefficient, plus this times the coefficient, plus this times the coefficient. This sounds like regression if I have enough of them, but not like regression if I have very few of them. Because regression puts a coefficient on every single feature value that you get. So, here's is that idea. It's an illustration here of how this stuff works. I'm trying to find a separation rule for these are my data points here, and these are the coordinates. Say this is the feature 1 and this is the feature 2, right? And they're numerical, and I'm trying to predict plus versus minus. But my trees are only allow splits by the features, right? So if I say if x1 is smaller than a value or bigger than a value, that's a separation that goes like this. And if I say if x2 is smaller than a value or bigger than a value, that's a separation that goes like that. For this illustration purpose, I'm going to restrict all the trees to be of one split only. They have a name. Anybody knows the name of the tree that has one split only? It's called decision stump. This guy. So when you hear the term decision stumps, that means a tree with one split. And that's it, stumps. So obviously I can't separate pluses and minuses with any horizontal or vertical line, right? How deep of a tree would I need to separate this stuff? I could say first separating here if it's bigger or smaller, right? I'm doing one line, and then in here I'm going to have another line here if it's bigger or smaller, and in here another line bigger or smaller, right? So instead, what this idea with addition of the trees is doing is saying if I combine these, so instead of having one tree that has level 2, which is what I will need here, right? I will need level 2 because I have what I said, the first line is this one, that's the first split. And then in the left side, I have these 4 points, I have to split them, this versus that. In the right side, I have those points down here, I'd have to split them around here to have left versus right. That's a tree now that has one split, and then each branch has another split, 2-level split tree. Instead, I can do this with 3 trees that are just decision stumps, single-level splits. Here's how. These 3 splits with coefficients, if you sum up black versus white, or in this case, dark gray versus light gray, 42% coefficient, that's this alpha 1 here. Plus 65% black versus white this way, plus 92% black versus white this way. How do I sum this up, actually? So how do I make a prediction of this? How do I know this is white, this point right here where my finger is? Well, I look at this point and say, what is it in here, in this first tree? White times 42%. In this tree is black. So that's 65% black, and then 92% white. So I say, is it more white or more black? More white, so then it's white. How about this one here? It's 42% white, 0.42 white, not percent. 65% black, 92 black, so it's more black. So if I can combine 3 trees of level 1 decision each, with additions, I get the full classification, which I could have gotten with a level 2 decision tree, right? If I allow my tree to be like this, I will obtain full classification. So what's the point of this then? Is it better to add up 3 single level decision stump trees, or to have a tree that's level 2 tree, like it has 2 splits? Is there an advantage of using a sum of 3 level 1 trees as opposed to using one level 2 tree? This is the kind of question you're going to get at an interview if you say I took machine learning. Since those two do the same, right? Clearly they do the same full 100% separation. Which one is better? One tree that's deeper or 3 trees that are shallower but combined give you the same thing? In terms of number of decisions, how many decisions are here or splits? 3. How many decision splits are there? 3. So is one better than the other?
It's faster.
Faster to train
Faster.
or to predict? Machine learning, you have to distinguish the prediction time versus the training time. I don't know if it's faster. I don't think it's significantly faster. But is it better as a machine learning algorithm? This is a standard question for when you say I took machine learning or I have experience with machine learning to test how much experience you have. Because people who run packages without understanding what they run will not know the answer to this question. But PhD students who study machine learning for research will probably know it. This is better. Because this overfits a lot less than a deep tree. A deep tree overfits quite fast. A deep tree creates small regions of data like this. Small region, small region, small region, small region. This mechanism does classification into those regions, that is true. But the regions for which the decisions act upon, each decision acts on entire data. And the addition of trees does not increase the overfitting. It does better for classification. It increases maybe overfitting a little bit. It has a very different growth of overfitting than growing a tree. Growing a tree increases your overfitting capability exponentially. Linear functions, like regression, right, doesn't overfit. It's easy to see why regression doesn't overfit. A line can only be a line, right? So whatever, it can rotate it, be in any position, but it's not separating points out because it's a plane or a line. It has to have two sides of it, right? So it has less overfitting ability, no matter how hard you train it, than. So this is the main potential of this method. There's another advantage in that by only doing shallower trees, I can, if the trees are greedy, so if my initial decision for the first tree is no good, a deep tree cannot change what's at the top of it, because once I make that decision, I cannot change it. But if I move on to another tree, how can I now compensate a little bit? I still gonna have this tree. So I already made this tree, it's a decision stump, and later on, maybe I figure out the decision tree, the rule that it has, the split, is wrong. How can this tree compensate for that? The second tree. I mean, it will not compensate, but in principle, in theory, that's possible. How can this tree say, you're wrong, buddy, we need to discard what you're doing. We need to, whatever the decision rule you have at the top is incorrect, I want to make it irrelevant.
Correcting the cut and
Because
making
that-
addition.
I can't change this alpha,
That's okay.
but I can make the second one much bigger. Right? To count a lot more on this. That's what happens here, this 92. So that's a way to say, I'm going to ignore what the other three was saying, because my coefficient is much bigger.
Or the mechanism to select split is basically like try all the possible split and select the best one.
Yes, but in here we need to do something very different to create those trees. Like how, we're not going to duplicate the trees, right? So I think her question, in effect, I'm going to translate it, is, wait a minute, if I have this tree already, the first one, how can I train for the second tree? That's in effect your question, right? I mean, it's got to be some sort of change in my algorithm. If I feed the same data with the same labels, how can I get a different tree out of it? So clearly this boosting, that's where the boosting key is. What do you change in the data after you train your first tree so that the second tree can do a different thing? In particular, to correct what the first tree got wrong. See, if I can train only one tree and get everything right, I can just stop, right? I have a simple decision rule. Simple is better. Occam's razor. The simpler explanations are the best. So if you can train a simple machine learning algorithm that does pretty good, do not do a sophisticated one. Stick with a simple one. That's a well-known rule, I hope. A simple tree is always better than a complicated tree if it does roughly equally well. The question is, once I have a simple tree, how do I come up now, how do I set up the second training for the second tree to kind of correct what the first tree got wrong? So I need a new setup, right, for this second tree. This class of algorithms, boosting or gradient boosting, can be extremely performant. Work extremely well. In fact, it's one of the main algorithms used in production a lot. Every time when deep learning doesn't work, very likely there is a called forest, you know, sum of trees, J forests, ensemble of trees, all these names refer to several trees that have an addition mechanism between them. So of course people now try deep learning on everything, sometimes inappropriately so, but deep learning is so well set up to run on massive scales, then it's perhaps easier to try deep learning than to think what the problem is. So people try deep learning, if it works, good, you know, not worry about nothing. But when it doesn't, the next immediate thing that you're gonna see, it's ensemble of trees, boosted trees, gradient boosted trees, all of that, it's something like this. So what would be a simple idea to use to set up the second tree? How do I set up the second tree? In fact, when I'm gonna say a tree from now on, let's imagine I'm training some machine learning algorithm, any machine learning algorithm. I say a tree, but it could be anything. How should I train a second one?
Forget about what you did in the first one.
So I have a H1. This is the first learning algorithm, right? So this is trained on data. It wants, what H1 tries to do is to map a X. X is the object, right? In my case, a document, of course, represented somehow, to map it into, to be approximately Y. Y here is the label set. Y1, Y2, Y, that's the task that I want to classify, whether they tags or relevance or something. That's what I'm trying to predict or to learn. So that's what the first classifier is trying to do. Say, I want to map the input into the output. If this guy has 100% accuracy, I don't need to train a second classifier, right? Suppose it does not. So sometimes it's wrong. How should I train the second classifier? This example is with decision stumps, which are simple trees, but you can apply this mechanism to any algorithm you have. Even if you have a support vector machine, you can do the same. Train the first support vector machine to do as well as possible. If it did very, very well, 99.95 accuracy, great. If it didn't, how would you set up a second support vector machine or a second learning algorithm to correct the first one? Yes?
All the data points which got classified correctly, you neglect them and treat only the ones which were not classified properly.
That will be very easy to do for the second classifier. The problem is you have no way to run that in testing mode. You're gonna get the data point, right? Document. Trying to train the first one. Now, you like to say, if this is correct, stop. If it's not correct, run the second classifier, right? to replicate what training did, except you're not gonna know if you're correct or not, right, after the first classifier. So that's a great idea, but
You try to figure out more correct labels using a second classifier.
more correctly, but how do I know what's more correct? So there is a very simple idea which works extremely well, and people have missed it for 10 years. People, I mean extremely smart people in the world. So I'm gonna give you the simple idea because that's obviously what you should implement or use. And then I'm gonna tell you for 10 years, people have been around the bush with very complicated stuff, when this idea would have been a lot easier. It took a statistician from Stanford University with a lot of theory. Even he didn't realize, but as soon as he published this new thing 10 years later, people have said, wait a minute, that's a lot simpler than what we have been doing. So here's the idea, very, very simple. What I want H2 of X to do is trace on the same data, all of it, not just the ones that are incorrect, but not to Y. It doesn't try to predict Y. It tries to predict Y minus H1 of X. In other words, the mistake, right? Or residual. That's obviously the mistake. If this is 0, means the first one didn't do a mistake, right? This one tries to predict the mistakes. Now, what would mean for H2 to be perfect? To H2 to always get this difference right? It would mean that if I add H1 and H2, I get Y, right? So the classifier after 2 steps, my main classifier, the combined classifier is H1 of X plus H2 of X. Because if H2 made some progress, then H1 plus H2 is now closer to Y than H1 was. Again, this works for every classifier. I'm saying decision trees, but they could be anything. This idea is called gradient boosting because it's trying to map to the H3 will try to get what? Be Y minus H1 minus H2. Now, I'm simplifying things because I want to translate the intuition first. There's these coefficients, right? Alpha 1, alpha 2. Where are those coming into play? You have to take a machine learning class for that. But that's how gradient boosting works. It always tries to predict a mistake. Now, this came later in a theoretical paper, but before that, people have recognized the potential of a linear ensemble of trees, except they didn't see it that way. The way they saw it was kind of like she did. The way they saw it was like, I'm going to run the first classifier. Let me see if I have those slides here. There somewhere. Right, so in here. This example, this is the same example. So I'm going to run the first classifier, and then in training mode, I know which ones I got right, which ones I got wrong. So in here, this is the plus side, this is the minus side. I know I got those 3 wrong. What she said was just focus on those 3, just classify those 3 somehow. And I said, I can't do that. But what this guy did is say, kind of decrease the weights. The ones you got right have a smaller weight for the second classifier. They're less important. And the ones you got wrong, they're more important. So I'm increasing the weight on those 3, and I'm retraining my classifier. Now that decision tree, the second one, has to take into account weights. Because now the data has, some points are less than 1 importance, some others are more than 1 importance. This is not a problem here. There's no weights in here. This X for the second classifier is the same data entrance as the first classifier. So if I increase those now, I get the second classifier. Say I get this classifier. And now you see how those are bigger because they were bigger increase from the first round. These are wrong, so I have to increase these weights. So I keep increasing and decreasing. I have now these two pluses and these two minuses. I got right both times, so they have very small weight. And these have right one time, wrong the other time. These are wrong the first time, right the second time, or no, right the first time, wrong the second time. So then when I run my third classifier, I'm going to force it to look more at those differences between now the points that are bigger. It's going to find this line, which has also some rights and wrongs. Every line gets 3 points wrong in here, no matter what. And then I combine it that way. This is a lot more difficult because weighting the data focuses very quickly on data points that are outliers. This mechanism here for weighting the data is multiplicative. So the actual formula, which is not hard, is saying take the weight that you have already, multiply it or divide it with a value. Everybody gets either multiplied or divided with the same value. And this is just normalization. So the new weight on data point I is the old weight, either divided or multiplied with something, and then renormalized to be a distribution. The problem is, very quickly, this focuses on outliers, which you always get wrong. So I'm spending a lot of time on data points that don't matter. And also I have to recompute those distributions all the time. This is much better and faster too. Gradient boosting. Another idea that fits in this second category is another powerful machine learning idea. This ECOC, it comes from coding theory. Here's my classes. This could be sports, economics, politics, whatever I'm trying to predict. I'm going to create a code for each class, a binary code. I'm not going to say how, but I'm going to create a code. And then I'm going to try to, instead of predicting the class, instead of training a decision tree or a supercomputer machine to predict the class, which is, again, 0, 1, 2, 3, discrete class. So this means it's not necessarily that 2 is between 1 and 3, just different classes here. Suppose I can predict F0, F1, F2 as labels, right? Pretty well. In other words, instead of targeting the class, I'm going to target F0, target F1, target F2, target F3. So I have, instead of one classifier, I have 1, 2, 3, 4, 5, 15 classifiers. I'm going to set it up in a way that this is easier to train than the class. But how do I use it in testing? I get a new document. I run all my 15 classifiers. So each one of them will predict 0, 1, right? So suppose I get 1, 0, 0, 1, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1, right? How do I make back this vector of 1s and 0 to determine which class is it? If it's exactly one of these, I'll predict that class, obviously, right? If it's exactly 1, 1, 1, 0, 1, 0, 1, I'll predict this class. What if it's neither one of these? I get some sort of string of bits that do not correspond to a class. That's where the coding theory comes into play. In coding theory, in transmissions and coding and encoding, very often you get a code that's messed up. So you have to correct it to the closest valid code. Memory reading and writing has a lot of these problems, right? You ever heard of this, what is it, the server memory? It's called, has a name, ECOC memory or something like that. Error correction memory. Never bought a server that has a special kind of RAM in it. That RAM corrects for 2 wrong bits. In other words, if every 16 bits you have 2 wrong, it can correct for them. The regular RAM that people have in their laptops and their phone can correct for only 1 bit. So if you get something wrong by 1 bit, which happens a lot, there's a lot of electrical signals that move very fast in there, you can easily get 1 bit wrong. The hardware corrects for that 1 bit because there's redundancy here. That same idea applies. If I'm close enough to class 4, but not exactly class 4, I'm going to predict class 4 and be correct. The server RAM can correct for 2 bits being wrong. So that has ability to have a lot more RAM in it, because if I use data that has 80 GB of RAM, chances are that 2 bits might be wrong when I read this matrices. So I couldn't do that with regular. So the same idea applies here. What I'll have to set up is to set up these classifiers to be easier to predict than the set of classes. Well, first of all, what's the obvious difference between these classifiers and the class as given? They're binary, the 2 classes, as opposed to that one which has 10. Right? So instead of predicting 1 class out of 10, each one of these classifiers will predict binary. I can also show with coding theory that if I produce here an F15 that's completely random, 0, 1, 0, 1, completely random, which a complete random classifier cannot be predicted, just overfitted. There's no way to predict something that's random, right? No matter how hard you try. You can overfit the data to try to get it right, but your chance of training a model on random data and then predicting correctly a random number, it's exactly 50%, right? If I train another one that's random, it's not gonna affect me at all. So even if some of these Fs are unlearnable, in machine learning, random means unlearnable. It's not gonna affect the performance of the whole ECOC setup. I only need few good ones, even if I have some that are not trainable. So what people do sometimes, they create random vectors, random Fs, and if only few of them are related to the labels, they can make the predictions. It also simplifies the binary versus multi-class problem. Many algorithms are much more set up to do binary classifications than to do multi-class classification. So that's ECOC. I think we should take a small break, and then I'll see you after.
not able to fix it.
You should not be saying this.
I need some time.
After doing PA now.
No, it's Gigi pattern. Like, I don't know.
Gigi pattern or Gigi plot?
Gigi pattern, the special plotter I used. Gigi pattern.
Gigi pattern.
Yes, I don't know how to use it. Like, I've given some values, there's something wrong. Like I do some data transformation, and now probably some cell value is so different that it's not able to take it, I'm not able to figure out. And I finished marking yours, the year
Hmm.
and I saw mine. So I'll probably finish mine today and then go for another position.
No, that's just it. I'm doing that. No,
Are your problems getting better?
No,
Getting worse?
no, it's not really resolving.
When's this gonna end, this saga?
I don't know.
Next term? Are you taking classes next term?
I don't want to at this point.
Would you?
I
have to?
tried dropping this. I missed it by a week though, because everything kind of started to fall apart like the second week of this, or the third week of
The
this.
situation in Boston or the living arrangements?
Yeah.
But next term you're gonna be okay?
What do you mean?
Like, are you still in school next term?
Yeah, I have one more course and then I'm done.
So, but you have to take the course next term.
Yeah, that's how I
And you-
graduate, but.
And you're gonna be from New Hampshire
you
coming?
told me.
That's your plan, or you're gonna find a place to live in here?
Maybe. I'm trying to figure it out.
It's not like I never tried,
So
I have
catch
tried,
up.
but then I figured it out.
But one course not that bad.
No.
4 months.
But
That's
I
fine.
work
Because I
80 hours a week.
Ah.
Yeah, that's what makes.
I have problems too, but I don't know if everybody owns a house or something like that. I don't understand how plumbing works. I mean, I do, but I don't understand how plumbers think. I somehow think, maybe because I'm a professor and I'm used to, my job as a professor, you'll be surprised, is, of course I have to lecture and keep you interested, but a big job as a professor is to put yourself in students' shoes and mind when they have a question or hesitation or
You mean not like that they don't
misunderstanding.
explain things to you?
Right, I have, my job is to put myself in your mind and figure out why are you stuck? Why are you not understanding this, or why can't you move on, you know? And then that makes it, if I do that, it makes it easier for me to give the proper answer. So I'm trying to do this with a plumber in my house. Why is the plumber trying to figure this out, and why it's so difficult? And I can't, for life of me, I can't figure out what's in their heads. Like, they're trying to explain to me how water and air goes through the pipes, and I'm pretty sure it's not going like they think. Like, I'm 100% sure. Like, law of physics will not be violated in the pipes in my house. Guaranteed. I don't know if they took a physics class, but it's just not gonna go that way.
Did you tell them
No, because
Why?
I'm afraid that they'll just
Screw up your house, that's
yeah,
what
give
you're
up
gonna
on me or something. There's some certain things that I do understand what plumbers do wrong, but I know why they do it, because they care about their job and nothing else. Like, there is a certain logic of where can you drill holes in a house. There's a certain, you can drill holes to here, to there, to there, to there. And while they do it legally, the problem with drilling holes is, of course, you weaken the structure of everything you drill through. And my house have some beams from like 100 years old. I would rather not drill to the beam and then see what happens, right? But plumbers say, you know, it's legal, so drill to it because it's not their house. That I understand. What I don't understand is this thinking about water and air and pressure. This is cold. I understand, I'm pretty sure that I understand how water works and gravity, but I'm also becoming confident that the plumbers do not understand that. I guess that's why the plumbing code is so complicated, because it assumes the plumbers don't understand physics. If they would understand physics, they wouldn't need so many coding rules for plumbing, right? Anyway. Okay. So, how homework 6 and 7 look like? Homework 8 is not gonna happen. 6 is the stuff that it has not a sparse matrix. The splitting on queries, here's a few queries, here's a few queries. Like we said in the one setup, I have 20 queries for training, 5 queries for testing. What are the rows here? In that setup, when I'm trying to learn, on different queries than the one I'm testing on, you shouldn't think of this as a document. This is really a document query pair. This is document 1 for query 5, right? So I'm not sure that's clear. If I set it up in this way, I'm trying to learn from the results of one query, the curl file from 20 queries, learn how to predict the curl for the other 5 queries. So in this case, what we really have is a query document line with features. Because the next line, it's another query document in the feature matrix. In other words, what I'm saying is I could have, theoretically at least, the same document. I may have, this is D1, I may Q1 D1, and this is Q2 D1. This may have a different representation than Q1 Doc1. Although this is the same document, the way we think about this as objects is a query document pair, is the query, that document for that query. This is different than this matrix here. This is a bunch of documents, and each document purely contains just the content information like the TF counts or bigram matches or trigram matches or whatever else. That has to be a different kind of feature. What says here in bold is you can't use unigrams in this feature matrix, because a unigram like China, I think it's an example here, right? It has a different meaning for query 1 with query 2. So in terms of, this is label is relevance. This is a 1, 0, 1, 1, 0, 0, 1, 0, so on and so forth, say relevance. These cannot be unigram features. These are going to be IR scoring functions. So this could be BM25. This could be a language model. This could be a page rank. And there's other pieces of information that you could put. Not all those pieces have to be related to a query. BM25 obviously is related to the query, right? Because BM25 is a scoring function. That's depending on the query. PageRank is not. PageRank does not depend on the query. But PageRank is a usable feature, because the importance of a page, it's consistent across all the queries. Problem with words like China is like China may matter for one query but not for the other query. So you can have a few basic scoring functions here, but you can also add some other things. Things like, what's the source of a document? Is from Wikipedia or from other places? I don't know. You're welcome to complete this, but this will not be a sparse matrix. Even if you get some things that are binary in nature, you get some zeros, this will not be a sparse matrix. So you don't have to worry about sparsity. And it asks you to do 20 versus 5. We tried in some years to do cross-validation, so you can split the 20s into 5 groups of 5, but I don't think that's what's being asked here. Because I think we would rather have you do the same 20s as training and the same 5 as testing. And so I think the TAs we have to clarify with the TAs which queries goes for training and which one goes for testing. These are well, this is split randomly.
Which label becomes 1 based on what relevance value? How do you decide that?
So if you have a query document pair, is the curl value for that query for that document, right? So the same document might be relevant for one query, but not relevant for a different query. That's why you may have for the same, even this is doc1, maybe one is 1 and the other one is 0. But the features will be also different because the BM25 score of that document for the query is different. Even if it's the same document, BM25 depends on the query. So this is an attempt to say, I'm trying to figure out from 20 queries how to train a model that will predict relevance for another query based on, of course, scoring functions. So if you remember, this is a fancy, from homework 1, this is in effect a fancy meta search technique. When we have a bunch of IR systems, those will be the columns, BM25 and so on and so forth, right? And if you want to combine them, well, we talked about, beginning of the term, you could do this CombMNZ or board accounts or simple combinations methods. This, in effect, is a meta search technique of combining the scoring functions that I have here, BM25, language model, PageRank, whatever else, combine them in a very, very systematic way with machine learning. This actually happens in both Bing and Google. Both Bing and Google produce all kinds of scoring. They don't have 10 scores, they have like 700 scores for recency, clickability, readability, content scoring functions like BM25, page rank information, something related with your history or whatever they collected about you as a user, all kinds of things. And in the end, there's a machine learning algorithm who runs through those 700 things and predicts relevance, how good the thing is for that query. So this is, in effect, a combination technique of how do I combine all these scoring functions into one main score. In machine learning, before information retrieval, this was usually called experts combination. How do I, or multi-arm bandits problem, when I have multiple inputs of one thing, how do I decide, how do I combine this advice from multiple experts into one action? So this one will not be a sparsity issue. For homework 7, the task is spam classification. So in spam classification, you're going to have a matrix like this, right? Because you get a document has unigram features, and based on these features, you're trying to predict spam or not. We have a data set that it has the documents, I think in raw form, so you get text, and the spam values. Not all of them, but most of them. So you can, I think technically you're supposed to sign an agreement and download that, but we have a version of it that you can get from the data resources probably. You should still sign that thing. That's a legal form. The data is free, but you should say sign up and sign the agreement. These agreements regulate what can you do with the data. Certainly running class experiments is allowed. So labels are in a different file. Spam and ham are the two binary labels, either spam or not spam. Now, this is asking you to do this exercise, machine learning for spam purposes, in 2 ways. It's the same matrix. You have to represent the documents in a bag of words representation. I think this is asking for unigrams, but you can add bigrams as an extra credit if you're interested. The problem with bigrams, again, does not affect machine learning. The algorithm will run the same. The the bigrams will increase massively the dimensionality of this matrix. The trouble with bigrams is not a learning trouble, it's a storage trouble. How do I generate this matrix fast enough, and where do I store it, and how do I access it? Because instead of 20,000 columns, I'm going to end up with 500,000 columns now. And if I add trigrams, that may be 7 million columns. So the issue with adding features like bigrams and trigrams or skipgrams, it's not a machine learning issue as it is a representation issue. But they're good. Some spammers, especially lately, unigrams alone do not detect spam that easily. The kind of spam that's being used now. So why is this written as two parts? The first part is asking you to guess the words that you read. So you don't extract all the unigrams. You have to put your mind at work for what unigrams I believe are related to spam. So I propose few of them in there. One is a bigram actually. How would this work? You come up with a list of unigrams. Let's say you would create like 20 words or 30 words that you think are mostly related to spam. And then how would you create this feature matrix once you have those words, those 30 words?
TF-IDF.
I mean, TF-IDF is okay, but you probably don't need document EIDF values. You can just do counts, TF counts. So you could either, if you have the data in Elasticsearch, query directly for those words that you have separately to get for each word I query, I get all the column, right? Or if you don't have data in Elasticsearch, you can parse it with a parser and just keep track of for each document, for each one of the unigrams, what was the count, and done with it, right? I'm sure Python has a library to do that. So in here, we are halfway in part one between machine learning, which is part two. Part two says use all the unigrams, let machine learning figure out which ones are useful. Part one, it's halfway between the doctors. Remember when I showed you those heuristic rules and I told you doctors and lawyers and carpenters and military people use heuristic rules like that just by trials and error? This is halfway in between. This is saying, I'm going to guess the words that matter, but then I'm going to let machine learning figure out the rules, like exactly whether they matter or not. I'm still training a machine learning algorithm who can figure out if I use trees, that if the word free appears at least 3 times, and I do not see that word, and I see the other word, then I conclude that's a spam document. So I'm still training a machine learning algorithm, but I'm guessing the partial representation of documents that matter. So then, of course, it's going to ask you to compare the results to see, okay, how accurate was your classification for the words you guessed versus how accurate is this classification if you use all the words. You can also try different algorithms. Since you're not going to implement the machine learning algorithms, you can try boosting or decision trees versus regression to see what works. Regression will work very well on the second part, because regression, like we already said, if you have a lot of features, regression is effectively having a coefficient per feature. So we're talking about 20,000 unigrams, 20,000 coefficients. That becomes a very complex algorithm. But for the first part, maybe regression is not so good because you only have 20 features. So the regression control is effectively only 20 parameters in there. I don't think it's that hard to run. It's 2 homework, 6 and 7. I think they can be done easily in a few days. One more thing. We have a method. We may not require this year because the double speed may be just easier to, when you extract all unigrams, some of you might find it easier to use a Python library to just extract all unigrams, so I'm willing to relax this constraint. There is an advantage, however, to do this with an index and with a function that works with the index, like we did homework 1. Remember homework 1, I asked you to specifically index and extract from their TF counts efficiently. We've developed such library. The reason for this is that when you go out in the industry and you work with somebody who has data, they will have an index very likely, maybe Elasticsearch may be a different one. But even if they don't have an index, the idea of parsing with Python the entire data to extract all the unigrams. See, if you only have 10 words, I can agree that parsing and extracting those 10 words of counts from all the documents would be a reasonable thing to do, although Python would be very slow anyway. However, if you try to extract all unigrams, or say unigrams and bigrams, with a lot of documents, this is not a scalable method. You know, Python will run out of memory before you can dump the feature matrix. That's similarly to how indexing works in homework 2, when we say you can't really parse all documents in a hash and they just dump the hash as the index. So for practical machine learning, if you go to work for a company that has a lot of data, and you need an efficient method to compute feature matrices from their data as it's stored already. That's not a hard thing, but more complicated than people think. To be able to extract this matrix really fast from data. And the advantage of inverted indexes is that if you're looking for TF counts or something like that, it's already in the index stored. So every column, it's effectively an inverted index already. So Elasticsearch or Lasso or Lucene, they already have it. If the people you work with have the data indexed, they effectively have the matrix. You just have to extract it very fast. So I've seen cases where machine learning algorithm took 45 minutes to run, but producing the feature matrix took 3 days. Because the implementation of how to get all the unigrams and bigrams from a large data set was very slow. Especially single-threaded ideas will be very slow. Okay. So what's left here? I would like to talk a little bit about naive Bayes. In a way, again, that even if we don't take a machine learning class after this, we understand the issue and the solution. Naive Bayes is not part of the homework, so I mean you can use as an algorithm. Oops, that's a third one that I'm dropping in here. At some point, somebody has to find a way to get everything. The general class of this method is called generative methods, or probabilistic. So what we want to do is to say X is the data point or document in our case, Y is the label, and Y belongs to a set of possible labels or classes or categories. We'll assume this is discrete, so this is a discrete set. We're not talking about salaries in here. We're talking about politics versus economics versus business kind of thing. So the purpose of machine learning, as far as generative methods go, is to have estimated the probability of Y given X. Right? If this is a set with, say, L possibilities, then I need, this is effectively what? This means probability of y1 given x, probability of y2 given x, up to probability of yl given x, right? So out of the possible classes, sports, business, economics, politics, so on and so forth, if somebody gives me a document, that's x document. What I want to do, of course, is to estimate the probability for which of the classes. And if somebody tells me you've got to make a prediction, what would I do? Pick the one that's highest, right? That's called argmax. Pick the one that's highest. Ideally, what will give me confidence if I make a prediction? Suppose I can calculate these probabilities. When I'm pretty sure I'm going to be right to make a prediction. When the high value is very high, and when I'm not so sure, I'll be right. When I have 20, say I have 20 classes, and each one of them is like 0.06, 0.04, 0.03, 0.07, right? They're roughly about the same. I'll predict the highest, but the highest is not that high. Versus if I have a 95%, the next one can be at most 0.05, so I'll be much more confident. That's a great advantage. This is, again, general machine learning. It's a great advantage of generative methods. If these probabilities are estimated correctly, even if generative methods will never be as accurate as discriminative methods like boosting and Lewis regression. If you want high accuracy, this is not it. But there is a great advantage in estimating these probabilities correctly. That is, linear regression or boosting cannot produce easily confidence or confidence intervals. They can fake it. I can pass linear regression to a logistic function and get a number between 0 and 1 if I want to. But that's a fake one. If I can compute this I get a much better sense of confidence in here. Okay. So what's the problem? Here's a bad solution to this. How to do this, right? This is a joint probability, right? P of y given x. It's a joint because x is really x1, x2, up to xd. So in terms of brute force estimating probabilities, in the sense of, you know, if I want to estimate how many people would graduate a course or follow a certain thing or something like that, I just look at the counts, right? Then I transform these counts to probability. That's how you can easily map a population into a density or distribution. But in here, if I do that brute force, literally asking how many times seeing an X like this, either identical or similar to it, I've got politics, versus how many times I've got economics, versus how many times I've had, you know, I don't know, the other classes. This joint is too big to estimate it by brute force. There's two problems. There's the fact that we don't have enough data. This is the D plus 1 dimensional joint probability, because it's D dimensions from X plus 1 from the Y, assuming 1 is a, you know, categorical attribute. So we're talking about D plus 1 dimensionality probability. Let's just make a gross estimation here. Assuming D is 100 dimensions, which is much more than our problem, right? We don't have 100 dimensions. We have way more dimensions than 100. But let's say it's 100. And each dimension has a few possibilities. So these are word counts. So it's between what? 0 and 10. How many possibilities are for this joint? Joints grow exponentially. The number of cells of a joint if this is 3 possibilities, this is 5 possibilities, this is 10 possibilities, it's 3 times 5 times 10. Right? It's like if I have 2 hats and 3 shirts and 4 pants, in how many ways can I dress up? Well, each hat goes with every shirt, with every pant, so then I have 2 times 3 times 5 possibilities. So you cannot estimate those joints in general machine learning by brute force. That's what the problem is. So too big for direct estimation. Okay, so then there's 2 options that we have here. What can we do instead? If this would be only few cells, we could literally count the data that fits in those cells. And then, so suppose I only have 2 or 3 dimensions, and each one of them has a bunch of possibilities, right? Then I can compute literally every cell of the joint, that is, what is the possible value for x1, times the possible value for x2, times the possible value for x3. I have, say, 300 possibilities. I could look at the data and say, for each one of these possibilities, how many times the points that fit in this cell were economics versus politics versus that, so I get the full estimation of the joint by brute force. There's 2 options. Either assume, so 2 solutions. Assume a model, typically a parameter model of data, and then estimate the parameters. So this is saying, I'm going to assume the data, this gigantic joint on so many dimensions, fits a Gaussian model. Because Gaussians are very nice, and mathematically they work so well. If I do that, I have to estimate now the Gaussian parameters. Right? Depending on the model assumption, I'll have to estimate what is the best mu and sigma in the case of Gaussian to fit my data. Or assume a structure of data like independence, and then estimate the joint based on that assumption. So those are the main generative methods that effectively any probabilistic method will have to make one of those 2 assumptions. Either model the data, say I'm assuming my data it's a Gaussian, Poisson distributed, exponential, it has the following shape, it has polynomially only 2, change of derivative, something like that. I make an assumption, and then based on that assumption, I estimate the best parameters within that class that will fit my data. I'm assuming most people have seen a Gaussian function, and there is an algorithm that fits a Gaussian the best it can to the data. You should tell MATLAB, I have a 300-dimensional data set, fit the best Gaussian you can to it. And it's going to give you the best mu and sigma for that fit. The problem with that is your data may not be Gaussian. Right? If that is the best Gaussian, MATLAB will produce the best Gaussian that fits your data. Not all distributions are easily fitable, but some of them are. There's no question that we don't know how to fit the model to the data. We know. The problem is the data might not correspond to the model. So that's not what I want to talk about today. What I want to talk about today is the second one. How can I solve this massive joint estimation by making an assumption, a structural assumption? Not that it's Gaussian or not a modeling assumption, but I'm going to assume that these x1, x2, xd are independent features, which is not true for text, right? If those are word counts, obviously, a document that contains the word nuclear is much more likely to contain the word atomic than not, right? So they're not independent. But if they'll be independent, how can we solve this? You guys remember naive Bayes? I mean, you do, because you took a class with me. Naive Bayes, how it works? Assuming a structure of the data, how can we solve this problem? Here's how. We want P of y equal x. That's what we want. Given a data point x, estimate the probability for a label. That is, of course, P of x given y times P of y divided by P of x, right? That we know for sure. That is P of y divided by P of x times. I'm gonna rewrite this, not x like this, but I'm gonna say who's x? X is a vector of the things. That's what x is, right? Given y. So this one here is this one here. And now I'm gonna make the independence assumption. I'm going to say this is P of y by P of x times how independence works. Probability of this conditional of these things given y becomes what?
The individual.
Index of y.
The what?
P of x1 given y to P of x2.
Into means times. So that is P of x1 given y times P of x2. I try to put the exponents of the features at the indices of the features at the exponents. I could rewrite this in a nice form. P of y divided by P of x times the product from P equal 1 to B of P of x t given y. Okay? So the question now becomes estimating each one of those things. That's easy. Who is P of x t given y? Can I do this by brute force from data? Let's translate this into English. xt is what?
The word count.
It's a word, right? Let's say it's the word China. Y is what?
Label.
Label, like economics. What is this asking in English?
Number of words that belong to it.
Label generated version.
Maybe the other way.
The number of words that belong to that label. I mean, the number of times the word is appearing in all the documents for that label.
Given only documents that have the label economics, what is the probability to see the word China? That's what this is in English, right? Because the label is a given thing in here. So we have to do this for each label separately. But that's still okay, right? If I just pull all the documents that are labeled economics, it's not hard to estimate this as a count divided by the total, right? I mean, it's a pure brute force estimation. It's nothing magic in it. I'm saying how many documents or how many times the word China appears. So many divided by the total, that's my estimate. So this can be estimated brute force directly from data. Okay? So that is in effect naive Bayes. This is an estimation from data direct. And then I'm making a product and I'm assuming the product is literally this, which is probably incorrect because those are not independent features. Now, let's think a little bit about this without going to statistics. This independence assumption. What is exact mathematical independence? What does it say? If x1, x2, xz are
Mutually
independent, then this is true. This equality sign. It doesn't say If they're not independent, this is not true. Are those equivalent statements? No. So it's a difference between A implies B, right? The other one is not A implies not B. That's not equivalent. Not B implies not A, it's equivalent to A implies B, right? So if the assumption doesn't hold, which we know for sure it doesn't hold, it doesn't mean this is incorrect. It's just not guaranteed to be correct. Okay? So the truth is, in many cases, this works, even though it's not independent. The estimation of this probability, I think, might come down to what you've done in homework 1 with smoothing. It may not be the best estimate to take the count divided by the total direct. Remember how we did in homework? I think in homework 1, we had the same problem, right? How do you estimate P, you take a count of a word in a document, how do you estimate this probability? You don't want to put directly TF by DL. There was some smoothing option there. That may be the case here too. We don't want to have a direct estimate. But that's, nevertheless, I want you to realize how much more doable is this estimated for every unigram against every label versus the size of the cell. The size of the cell is an exponential growth in the number of dimensions. Like I said, it's how many possibilities are for x1 times possibilities for x2 times. That's a huge number. While in here, if I have even 10,000 words by 20 labels, I'm talking about 200,000 estimates. It's much more doable. Now, one more thing. What happens with P of X? Because I talked about this product here. But what about those two things? Who's P of Y? Hmm? Yeah, the Y is a label, but
The probability, I mean,
what's P of Y?
Among all the labels, what's the probability of having this label?
So that has a name.
What's TD?
That's a prior. P of Y is a prior. So it says how many documents, absent of any information, what proportion of documents is economics? What proportion of documents is politics? Of course, that's independent of the features. It's not like dependent, right? So that's a prior. How do I measure this? I just look at my data and say, okay, well, what percentage of them is that? How about P of X? I need P of X too. Right? Can I estimate how likely is to see a data point, independent of the label, right? Because that's what's saying, how likely is to see an X that has the following features. That word so many times, that word so many times, that word so many times. How likely is to see such a document?
And then you compute it from the data.
That's hard because it comes down to a massive joint, right? That X is a d-dimensional joint. It's not d plus 1 because it doesn't have Y, it's just d. So there's a huge number of possibilities, right? Even if I have a big computer, which I don't, nobody has. The problem is there's not enough data. You can't estimate every single possibility. Simple. Most of the possibilities for X, that word appears so many times, that word so many times, are invalid documents, right? Most of the cells in this joint talks about having a certain word few times, having a certain word some other times. And if you look at the counts, it would be like, no documents will have this distribution of words. That wouldn't make any sense. We know that for sure because the number of cells in this joint is much bigger than the total number of documents ever written or ever will be written. So most of the cells make no sense. They complete zero. We can't do that. So how do we deal with this P of X?
Ignore.
but isn't it the same for,
Right. If we only look at R max, right, we don't need P of X because in terms of R max, which one is the maximum probability Y all y's, all possible labels will have the same p of x, so it's proportional. So in terms of getting their max, this is not needed for arg max. So to get what's the highest y, highest probability y, that's arg max, I don't need this. However, if I don't have p of x, I can get the arg max, but what's going to happen here with the probabilities? They won't be the right probabilities, right? Because they're not normalized by the proper x. Can I go around this thing somehow?
You don't need a right one, you just need the maximum.
Right. To get the y, if I make a prediction, I could say the highest probability is for the class economics. But if somebody asks me, what's that probability for the class economics, I won't be able to say. Can I figure out somehow a way to get back the right probabilities without computing p of x? Or maybe computing p of x, but not that way. So if I don't do it p of x, I get a probability for each class, right? That's a fake probability because it's not divided by p of x. What should happen with these probabilities? This one, and all the way to the end. Should they sum to 1? Under the assumption that the document must have a label. You should think about that. Some problems come with the document has no label at all. Maybe that's a possibility in itself, no label. But if one of them must happen, can I say, well, okay, I compute it without p of x. I get these values, and then I normalize, I divide by the total, would I get back the total probabilities? The correct probabilities? In other words, what I'm trying to say here, is it true that p of x can be computed as a sum of these unnormalized things, in effect? Is sum over p of y times p of x and y unnormalized I think that's true. You need to go back to the probability basics for this. Like in other words, if I, this is called a sum rule. It's saying x fits in one of those categories, and the total mass of probability of x, it's the probability for each class times the probability x being from that class. That's the total max of x. Like all the documents that have this label, all the documents x could be from label economics, politics, so on and so forth, and that's how it's computed. So I can get around this problem without computing x, again relying on how good those estimates are, get back to the estimate of x. How can I do a sort of naive Bayes? Now, suppose the independence really breaks up the problem for me. Naive Bayes doesn't work, and I'm sure it's because of the independence. Can I do some sort of naive Bayes, but not so independent? That's the last thing I'm going to do today. How can I do this thing? I like naive Bayes because it breaks up the probability estimators into probabilities that are very easy to estimate. But it makes this independence assumption, which can kill me. Can I do something in between to still use this mechanism, but not be forced into such an independence assumption? I think what she's proposing is instead of this product, right? That's the independence assumption. How about something like what do you say? P of x1 given y times P of x2 given y and x1, like that, times P of x3 of given x, y, x1 and x2. Yeah, this will be correct. This is not using any assumption. This is P of x, the whole x1, x2, xd given y. That's how conditional breaks. The problem is, as I move further and further, this is still a massive dimensional joint, right? Once I move down this path, by the time I'm in the middle, I have a half d by 2 dimensional joint, way too big. So still a big dimensional joint to estimate here. How about we try something like, I'm gonna guess somehow in advance, if I can, what features are dependent. Suppose I have a way to say, you have those words, right? The features are words. Suppose I say, I know that, you know, nuclear and atomic are related words. Nuclear, atomic, bombs, and I don't know, fusion and fission and Hiroshima are all related words. How can I still use naive Bayes or something like naive Bayes, but not break those words into independent estimators, because I know that's wrong. Can I say estimate x1, x2, x3, and x4 given y times probability of x5 and x7 given y times probability of x6, x9, and x12 given y, so on and so forth, where these are dependent groups. These are dependent features. If I do something like this, naive Bayes independence come into play how? What's my independence assumption here?
All similar words are different from each other.
This group is independent from this group, but I'm still allowing dependencies inside the group, right? I'm saying I don't want to break those apart because those four are dependent. I'm going to estimate it as a joint. I have to be careful, like I said, when joints grow big, brute force is impossible. So can I estimate a group of 3 or 4 together? Maybe I can, comes down to the same problem as skipgram. Can I run a skipgram? This is a very powerful mechanism if you can figure out in advance the grouping. So you need a method to estimate what features are related. In IR it's easier than in other places because we deal with words. There's so many dictionaries, ontologies, word vectors, you name it, that could tell you, hey, the following 6 words are related. So you can set that as a group, right? If you could do this, you get much better performance than naive Bayes by independence. And it's not too hard. The joint estimators could still be only few words that are very related, right? You don't need to have a lot of words in one place. Okay, so that's what I think we will stop. Next time. So I think this is what you need for homeworks, this 6 and 7. You don't need more than this. So next week I'm going to talk about some things that are over the homeworks, but no homeworks for them. I can tell you right now what I'm planning to do. I'm planning to talk about word vectors a little bit. I think all of you have heard the word vectors and perhaps know what they are. I'm not going to talk about how to estimate the word vectors, but rather, once you have word vectors, what are they good for? Topic modeling, that's a core IR issue, but we have no homework on it because the homework would be too complicated. We have a data mining homework for it. And perhaps some history of Google and how search engines evolve in time. But next week, I think, is the last week of classes. Is that right? No? Is it? Or not? That's what I think. Is the last week of classes.